In this video, I am going to go through how to balance chemical equations. I'm going to go over several examples and give you hints and strategies to follow whenever you run into any difficulties. Remember that when we balance a chemical equation, what we're really trying to do is adhere to John Dalton's idea that chemical reactions really simply involve the rearrangement of atoms. And we're going to reconnect them, join them up, bond them in a different manner than they had initially been in. Because of that, the number of atoms that were present at the beginning should be equivalent to the number of atoms that are equivalent at the end. So let's keep that in mind as we go through these examples. The first one, here's a word equation for some reaction. Sodium is dropped into a beaker of water. You get two products, sodium hydroxide and hydrogen. So first of all, we need to write out the correct formulas for the reactants and the products. Sodium, obviously, is just Na. Water, we all know, is H2O. Those are my reactants. And the products, sodium hydroxide. So sodium is 1 plus, hydroxide is 1 minus, so that's the correct formula. And then hydrogen, I have to remember that hydrogen is one of my diatomic molecules, and so the proper symbol, of course, is H2. So in this one, a little strategy here. It's a fairly simple reaction, and the equation shouldn't be that difficult to balance. But just a little clue here. I can see that on the left side of the equation, if I focus on hydrogen, whatever coefficient I put in front of the water, I'm going to multiply it by 2 to get my total number of hydrogens. And any number multiplied by 2 gives me an even number. On the right side, however, there is an odd number of hydrogens. So I'm going to strategize, and I'm going to try to put a value, a coefficient in front of the NaOH that will generate an even number. And the simplest one, of course, is to put a 2 there. So now on the right side, I have 4 hydrogens total. So that means I can go over to the left side and put a 2 in front of the water, and now I have 4 hydrogens on the left side also. Now when I put that 2 in front of the water, that gets distributed also to the oxygen, so there are 2 oxygens. And if I check the other side, though, that 2 I put initially in front of the NaOH also gets distributed, and I've got 2 oxygens over there too. So I'm okay on the oxygens and the hydrogens. And then finally, of course, on the right side I see 2 sodiums. So on the left side I'm going to have to put a 2 out in front of the Na. And now it's balanced. So solving that problem in particular, involved a little bit of strategy so that I could kind of get started on it, and then once I get started on balancing one element, usually the others will balance fairly readily. Here's a second problem. Again, I'm giving it in words. You're going to have to translate it. Aluminum sulfate solution mixed with a calcium chloride solution. The test tube immediately gets cloudy, and both aluminum chloride solution and calcium sulfate precipitate are produced. So, starting with the aluminum sulfate, aluminum is 3 plus, sulfate is 2 minus. Common multiple of 2 and 3 is 6. And so I need 2 aluminums and I need 3 sulfates. It's a solution, so I put AQ to tell you that. My second compound, calcium chloride. Calcium's in group 2, it's 2 plus. Chloride is in group 7, it's 1 minus. I need 2 chlorides to balance out the charges. And again, it's a solution, so I put AQ. Now let's go to the reactants. The first reactant, aluminum chloride. Now notice the subscripts on the left side do not have to match up with the subscripts on the right side. I'm going to get the subscripts by looking at the charges again. So aluminum is 3 plus, chlorine is 1 minus, so this time I need 3 chlorines. Now, if you look at the left side, there are only 2 chlorines. Don't worry about that at this moment. Get the right formulas first, and then we'll balance the equation. Aluminum chloride's a solution, so again I put AQ to tell you that. And my final compound, my precipitate, calcium sulfate. Calcium is 2 plus, sulfate is 2 minus. That's a solid, so I put an S there to tell you that it's a precipitate. When you're balancing this, the polyatomic stay together all the way through, so you don't need to separately deal with the sulfur and the oxygen. I'm going to balance the sulfates. So I saw that there were 3 sulfates on the left side because of the subscript. So to get 3 on the right side, I put a 3 out in front as my coefficient. And of course, when I put that 3 there, it changed the number of calciums because it, of course, gets distributed. So on the left side, I put a 3 in front of the calcium chloride. But again, that 3 also gets distributed to the chlorine, and 3 times 2 is 6. So I need to get 6 chlorine on the right side, and by putting a 2 out front of the aluminum chloride, I get my 6 chlorine. Now when I put that 2 there, again, it gets distributed, and it affected the aluminum. But I needed 2 aluminum anyways, and you can see on the left side, I've got Al2, so it balances. So this example, if you have a polyatomic that does not break apart, it is perfectly fine to balance the entire polyatomic ion. If you want to, you can look at the individual components, but it's not necessary. A third example, ethane is mixed with oxygen, ignited, and I get carbon dioxide and water. So ethane, obviously, is my first reactant. That's going to be the fuel. For anything to burn, I need to add oxygen. It needs to mix with oxygen. And I have to remember, oxygen, again, is one of the diatomic molecules. On the right side, my 2 products, carbon dioxide, obviously is CO2, and water, of course, I've run into many times. In this example, we're going to leave oxygen to the end. If you have an element that's all by itself, like oxygen is on the left side, leave it to the very end, because I can put any coefficient in front of the oxygen and it won't undo balancing of the other elements. I can put whatever I need there. So let's start with carbon. There's 2 carbons on the left side. To get 2 on the right side, I'm going to put a 2 in front of the carbon dioxide. Now let's do the hydrogen. There are 6 on the left side. To get 6 on the right side, I'm going to put a 3 out in front of the water. So I've got my carbon and hydrogens balanced. I just need to take care of the oxygen. I look at the right side. I distribute the 2 times the CO2 to get 4 oxygens from the first term and 3 oxygens from the second term. That's 7. And on the left side, whatever I put out front has to get multiplied by 2. So 2x equals 7. I knew I had to put a 7/2 there, or 3.5. Right now, this equation is balanced, but we prefer not having fractional coefficients. So like you do in algebra class, to get rid of fractional coefficients, I'm going to multiply, in this case, by 2. The entire equation gets multiplied by 2. So when I do that, my new coefficients are 2, 7, 4, and 6. Whatever you do to one term, you got to do all of the terms. So that's a little clue. I did 2 things there. I left oxygen to the end, and I used a fractional coefficient momentarily in order to get it to balance. But I eventually got rid of the coefficient by multiplying by 2. Let's go to a 4th example. Tetraphosphorus oxide is mixed with water, yielding hydrogen phosphate. Well, tetraphosphorus, well, tetra means 4, so there's going to be 4 phosphorus. Decoxide, deca means 10, so the formula is P4O10. Mixed with water, obviously H2O. And on the right side, I've got hydrogen and phosphate. Hydrogen is 1 plus, phosphate is 3 minus. So the correct formula is H3PO4. Don't confuse hydrogen phosphate, the compound, with hydrogen phosphate, the ion. This is not an ion. They didn't refer to it as an ion. All right, I've got oxygen everywhere. So let's leave oxygen to the end. If it's everywhere, I don't want to start with it because I'm going to end up going in circles. So let's go after the phosphorus. There are 4 on the left side. So to get 4 on the right side, I'll put a 4 out in front of the phosphoric acid. Then I can go after the hydrogens. So on the right side, distribute the 4. 4 times 3 gives me 12 hydrogens on the right side. To get 12 on the left side, I'm going to put a 6. 6 times 2 is 12. More than likely now the oxygens are balanced. And if we look at the left side, I've got 10 in the first term and 6 in the second term. That's 16. And on the right side, 4 times 4, when I distribute the 4, is also 16. It balanced out. All right, let's go to a 5th example. Methanol is poured in a dish and ignited, so it sounds like it's a combustion reaction. And of course it reacts with oxygen, and I get both carbon dioxide and water evolved. So my fuel is the methanol. I remember that oxygen is diatomic, and on the right side I've seen carbon dioxide several times. I know water is H2O. So once again, I've got oxygen all by itself, so let's leave that to the very end. So let's start with the carbon. On the left side I see 1. I also see 1 on the right side. The carbons are set. On the left side, I see 3 plus 1. I see 4 hydrogens on the left side. To get 4 on the right side, I'm going to put a 2 in front of the water. Now let's go after the oxygen. On the right side, I've got 2 in the carbon dioxide, and I've got 2, once I distribute the 2 out in front of the water, so I've got 4 oxygens on the right side. On the left side, I've got 3, but I don't want to look at it that way. I probably don't want to change the coefficient in front of the first term. So therefore, in that term, I've got 1 oxygen. That's already accounted for. So I need 4 minus 1 is 3. And so I'm going to get the last 3 from the second term. And 2 times x equals 3. My coefficient has to be 3/2, or 1.5. All right, so you notice what I did there. I counted the oxygens in the term that probably was not going to change. I subtracted that from the total, and the remainder I got from my oxygen term. This time it required a fraction. Again, I don't like fractions. I need to get rid of that 3/2, so I'm going to multiply the entire thing by 2. And once I do that, I get 2, 3, 2, 4 as my final balanced equation. All right, so those were 5 quick examples that I provided some strategies to help you when you're trying to balance chemical equations.